Okay, so welcome to this session. I'm going to introduce Professor Atlas Wang. So he's currently assistant professor and fellow of the Jack Kirby Texas Instruments Endowed Faculty Fellowship in Computer Engineering in the Department of Electronical and Computer Engineering at University of Texas at Austin. So he was a assistant professor before of computer science and engineering at Texas A&M University. He received his PhD degree from ECE from UIUC in 2016. So Atlas Wang has in-depth knowledge on the algorithmic innovation in graph deep learning. He's broadly interested in the field of machine learning, computer vision, optimization, and their interdisciplinary applications. His latest interest focuses on automated machine learning, learning-based optimization, machine learning robustness, and efficient deep learning. His research is actually broadly funded by NSF, DARPA, ARL, ARO, as well as a few more industry and university grants. He has received many research awards and scholarships, including most recently an ARO Young Investigator Award, an IBM Faculty Research Award, an Amazon Research Award, a Young Faculty Fellow of TAMU, and the Fall Research Competition Prize from CVPR, ICCV, ECCV. Those are the top conference in computer vision. So now let's welcome Professor Alice Wang.
Okay, thank you, Ying, for the introduction. Let me see again if I can still share. So the screen looks okay, right?
Yes.
Okay, thanks. Okay, thanks for having me here. So actually, as Ying introduced, I primarily was the head of a faculty member at UT Austin, but in my 20% time, I also work for Amazon, and I'm currently a visiting researcher at Amazon Search, and working on interesting science problems on search and ranking. So today I actually will wear my hat as an Amazon as an Amazon research scientist and talk about the work done with my Amazon colleagues and my intern also student. So this work, inductive graph neural network for transfer learning, was done in collaboration with my PhD student slash intern Wenqing Zheng and Yan Han, and also my colleagues Nikki Rao, Eddie Huang, and Catherine Suban. Many slides are kindly offered by Catherine. So let's warm up a bit first with our problem background. So in Amazon, we are interested in distilling behavior signals from search. And by behavior signals, that could be very broadly referred to which customer want to buy what item, which search keyword a customer would use to find what item. So those behaviors associated with a successful search and purchase behavior. So every day we have a big catalog, and there are millions of new parameters in Amazon we call ASINs being added to this catalog. And because they are new, those ASINs often do not have user-related behavior signals. For example, an item when newly added into the catalog, maybe no user have ever purchased that, so we don't know who will buy what. And for the same reason, no user has searched for that, and so we don't know what will be the search keyword. That created the so-called cold start problem, with very classical in recommendation system. And this is very significant for business in e-commerce platforms, including Amazon, because we have new product and we are expanding new market, and that lead to a very long tail of such cold start items in our dataset that we need to improve our recommendation, search, and ranking performance. So our goal would be to use machine learning solutions to increase what we call the product type signal coverage to either acquire or estimate the behavior signals of the newly added items. And those behavior signals need to be estimated from users in a certain market and items in a certain market. So that is our problem. And recently, we know that a graph neural network has achieved state-of-the-art performance in node classification, regression, and also recommendation system tasks. So it is a very natural tool to build a pairwise relationship And assuming, for example, we're only interested in the behavior relationships between customers and items. So those could those could so they can both of them could be viewed as node categories, and they could be connected together by a bipartite graph. And then we could use graph-based tools to solve their relationship. For example, estimating the link between a user node and a user node and item node could be considered as a classical link prediction problem in graph. So graph neural networks are great tools to achieve such kind of task over the user item graph. However, most modern GNNs rely on the principles of message passing. That means they will need existing links to aggregate each node's feature from its neighborhood, one hop or multi-hop. So therefore, the success of modern GNNs critically rely on the presence of good, high-quality connections within each node because it needed to read information from the neighbors through the existing node links, and then aggregate and then do that iteratively. So here are just some math for that. So GNN can work really well when such rich and high quality connections are available. But when we want to apply GNNs to those nodes with a small amount or even no skip connections, that become a chicken and egg problem, right? Because we want to, our goal may be to estimate the missing link, do link prediction. But some node has no link at all, and then how GNNs is supposed to work there? That lead to the cold start problems also in the graph type models in general. So a practical barrier of the widespread applicability of GNNs, as we already mentioned, arises from the long tail node degree distribution existing in many large-scale real-world graphs. So specifically, the node degree distribution is often parallel in nature, with a majority of the nodes have very few connections, less than 5 or sometimes even 0. So this figure illustrates some long tail distribution we calculated from we calculated from several averaged from popular dataset, and the right one was dataset specific statistics. You can see that there is a large range of nodes which containing less than 0.1% or even 0.1% of link from the richest ones. So it's quite imbalanced. And especially of our interest are some nodes with absolutely no connection at all. For example, in this rightmost end of the tail. They are called strictly cold start node. And this problem is the hardest in both GNN and recommendation system. So many information retrieval and recommendation tasks face those scenarios of a strict cold start, dealing with those zero node, and they seem to be fatter for graph-based method, nothing to aggregate. So what we can do, right? So for this general problem of cold start, not necessarily strict cold start though, but for cold start, people has adopted method in inductive graph neural network approach. For example, the classical inductive graph method maybe people may come in mind was Hamilton and others, the graph sage approach. This existing method learns a function of node feature and node neighborhood, and that can transfer to unseen graphs. However, that would require the neighborhood to be present during inference still, and that assumes robust aged similarity between training and testing. So that is good to have, but that does not exactly solve the strict cold start problem. And also it faces the transfer gap when the graph becomes significantly different. Now strictly in the context of cold start, in the recent 1 year maybe, so people have started considering the cold start problem more like a transfer learning approach. So the transfer learning approach here could be roughly thought as if we have graph with both warm node with lots of connections and cold nodes with a small amount of connections, we could first pre-train our graph neural network in some way over the warm part, those with a good amount of connections, and then somehow transfer its performance to the cold ones and using some methodology less dependent on message passing. So that transfer approach is based on partitioning the graph itself into the high connectivity and low connectivity portions and consider them as a source and target domain. So in that transfer learning context, Some method has used some method has focused on use knowledge distillation method. However, those knowledge distillation, which first train graph on many of them first train a graph neural network on the source domain and use it to improve another smaller graph neural network on the target domain. That improves the node and link prediction performance when the node connectivity was small but non-zero. But still, it does not address the case of noisy or totally missing neighborhood in the code part. One particularly interesting approach I would like to refer to is called Graph MLP, published in last year News. This is particularly interesting because they directly train MLP over the entire graph that only takes node features and do not do the message passing at all. The way they have incorporated the graph structure information is to re-encode the graph connectivity as a contrastive loss, which is a loss level encoding of who is near and who is further away, but it does not use message passing. So in this way, it does not require during the testing stage, the structure of graph links are still there. So it's a pretty aggressive and visible trail. They directly use a node level MLP to replace the graph neural network. And surprisingly, they find it performs okay, although it does not really outperform the graph neural network when there is link, but it gives us important inspirations that at least in certain cases, MLP, the node MLP on a single node is not a very bad baseline. So those are the prior arts in this field when we start kicking it. So we have absorbed several prior wisdoms from them. On the one hand, we are interested in the transfer learning idea because that fits our scenario from head to tail. And we are interested to improve the tail by borrowing knowledge from the head, the warm connections to cold connections. And on the other hand, we have to face those totally noisy or zero connected node problem where no GCN would ever be useful. And the graph MLP give us good inspiration. So in order to blend those ideas, we try to consider how we could for those because we know some of those code nodes will have no structure at all. We want to see we consider the graph's information to be the three vertices of the triangle, the label, which is our target, the feature which belong to each node, the structure which is often encoded by link. So let's consider this triangle of graph information. Okay. So for the head part, we have both a feature, node feature, and the link structure, and we are only about to estimate the label. For the tail one, it's a bit unhealthy because we don't have the structure, but we still have the node features. So in order to better estimate the label, is there any way we could estimate the structure first from the node features, and then still use the same principle to aggregate node and to aggregate node and structure information to estimate label? So the research questions become: can we benefit the code start node by first estimate its structure to fill in its structure gap? So inspired, so let's first look at a bit theory which inspired how we design our method. So this is the feature and label smoothing theorems from Wang and Laskovich in their 2020 paper. So skipping all the mathematical details, in plain language, this theorem basically tells us the error of label predictions are determined by the difference between the features after neighbor propagation, the difference of the features after neighbor propagation. So you see, this is after neighbor propagation feature, and this denotes how I aggregate features from my neighbors, use some coefficient, and this is my target feature at this step. And they usually have they have an error with each other, so those are all assumed to be optimal features. The optimal neighbor features after linear combination, and it will still have this epsilon difference with the optimal features x at this step. So this is considered the error for feature structure correlation. That is, how much we cannot, how much gap we have in estimating the node purely based on its structure. So it has been found that for the densely connected node, this epsilon is in general very small. So structure have contained most of the information. And for the cold start node, because you don't have structure, so this term is very inaccurate, and this error term will be very large. So we could consider the node feature and the link structures to have a mutually complementary role. If you have good structure, then structure itself could do the prediction very well. So this term is strong and this term is very small. But if you don't have good structures, this term is very weak, and this one you have to pay attention to. And the error, if you don't do anything, it will be large. So inspired by this observation that we already know for cold start nodes, this one gonna be weak. If we don't do anything, this term gonna be large, and this feature will be inaccurate because for normal message passing graph neural network, you will have no way to know what's the ground truth this epsilon signal. We have done the following model. So we are inspired to develop the following structure that we call error compensation for this label smoothing. From a high level, you can think like this. We will first learn a feature. We will first learn a mapping from the node features to the epsilon, where we call the structure encoding. And this does not dependent on the neighborhood of this node. So specifically, we want to learn this epsilon instead of just let it alone. Because in classical graph neural network, you have no way to estimate it. You can just let it go and hope it to diminish during the information aggregation process by this term and this term getting close. But we explicitly admit this term you will not be able to ignore during the training, and we wanted to directly estimate this error term from my current feature X. Even this term is not good. So we want to build a mapping from this term to this term. Even this term is not good. That's what we mean by structure encoding and purely mapped from the node features without depending on the neighborhood. And if we could estimate this error term, this becomes error compensation of the imperfect neighborhood aggregation, and we are just add this term together with the neighborhood aggregation to estimate my feature. Assume I always know this error accurately, then even this neighbor is not good, I could still let them compensate each other. That is the main idea inspired by this theorem. So how we learn this structure encoding? So our approach follows the idea of teacher-student distillation model. We do the following. First, we train a teacher model, and this teacher model is trained over the warm part with abandoned node connections. And this way, we will have the teacher node to estimate both its node features and the error structure encodings. And the teacher model can then be applied to the code part, the student model. And the performance will not be good. But our goal to apply this teacher model, which is a graph neural network, on the tail part will have no skip connection, will have no graph links. We know the performance will not be good, but our main purpose of doing that is to let the teacher estimate the structure, the encoding term, which is the bias term here, the error compensation. We want to let the teacher estimate the error compensation over the cold start part, the tail part, the part without a good skipping connection. So that become a bias and an inductive bias we want to pass from the teacher to the student model. So once the student have taken over this structure encoding term from the teacher, it will use this term to compensate as error propagation, even the implicit neighborhood isn't doing good. So it will imitate this structure encoding and aggregate features as they have, because they may not have, and then do the prediction again. It does not imitate the prediction output of the teacher model, but just the inherent information from the structure encoding the error compensation term. So you may be here. You may have a question of confusion. Why I would need to retake the structure encoding from the teacher and have another model to do that? Why I'm not directly using the teacher model? Well, the big deal here is for the student model, we realize that if we do not have precise neighborhood, we would rather not use the neighborhood. Instead, the teacher model will be a graph neural network, aggregate structures, and estimate this error compensation term. The student model will totally give up using a graph neural network because I know the neighborhood is not good. It's the part of data is on the tail. Instead, we will just use a graph. We will just use a node level MLP, multi-layer perceptron, which takes the node level features as input, structure and the target as output. I will only take the structure encoding encoded from the teacher, but I myself, the student model, will not take in any explicit structure information because now on my part of data, that structure link connections will not be good. So summary our ideas on the high level. First, we will have a teacher to estimate the error compensation, not the predicted target for the tail part and pass to student. Second, the student will use a MLP, not a graph neural network, to estimate the tail part because this part has no good structure. Those are two important take-home messages. So to make it a little bit formal, so we have that here. Well, I hate to put notations in slides, but here sorry, I have to put some here to just to give you some precise descriptions. So here we have the graph adjacency matrix A and the normalized adjacency matrix A bar. So the lambda presentations at each layer is denoted by the super index, and the node index is on the lower index. And we will do the inductive node classification problem. For example, actually in the experiment, we have tried it to work for also link prediction. So we know that our graph will have a lot of cold start and isolated node. So the teacher model here will be a graph will be a graph neural network model. We usually don't do it deep, just a two-layer graph neural network model. So it take into account the normalized structure, the weight, and do that hierarchically. The main goal of this structure that teacher learning is to estimate this E. So this E was the error compensation term that we pointed out in the label propagation the label propagation theorem a few slides earlier. So if you still remember, we discussed the error relationship between when you have this good this good aggregation, then this error doesn't have to be big. When you don't have a good error neighborhood aggregation, this error has to be compensated. And here we institutionalized this relationship by setting this error per error compensation term as a learnable bias for each node. So notice here, for each node, we assume it has its own error compensation. Here we give it a name called structure embedding. So note this looks pretty similar to a bias term in graph neural network. But the key differences here is this bias is learnable per node instead of shared all the overall node. It is a node level parameter rather than a model level parameter. So I would like to further point out that this existence of this structure encoding also avoid the over-smoothing issue in graph neural network, because now the transformations applied to different nodes are no longer the same because each node has its own structure encoding bias. So it also helps us to train deeper networks, although it's out of this project interest, but it may be of interest to other independent studies. So as I stated, the main goal of teacher model is to estimate this term, the error compensation. And then we will use the two MLPs. We will use MLPs in student model, and specifically, we actually use two MLPs. What we do is we have the first MLP to imitate the relationship between the node features and the structure encodings. That's what I mean by teacher-student here precisely. So on the part of node where teacher model can be applied, for example, teacher model cannot be applied for zero connected node, but maybe it can be applied for connections more than for node with more than 10 connections. We will have an empirical bar there. So the teacher model will first be applied, and then all the node after applying the teacher GCN model will have such a error compensation term, this structure encoding E. So this one comes with one structure encoding every node. So this is a learning product we want from the teacher model. And then for all the nodes currently being assigned with the structure encoding, we will use the first MLP to build the mapping between its node feature and the associated structure encoding. The first was supplied by the graph. the output was supplied by the GCN teacher. So this F1 is an MLP. So we want to first do a node level relationship between the features and its error compensation term. And once we have learned this mapping, we could apply this MLP to similarly estimate the error compensation term for the remaining node where the teacher's GCN cannot work on. Because now we just have an MLP, it only consumes the node features, so it can be applied even to the cold start features. And then after we are able to obtain the error compensation, the structural encoding for the even cold start and strict cold start node, we will apply it to give a structural encoding to everybody and use a second MLP, which follow the idea of graph MLP to be applied to the tail part. The reason we use a graph MLP is we find that on the long tail, MLP indeed performs better compared to graph neural network because by then the graph structures is not trustworthy. So the teacher-student model, our student actually use a two-stage MLP. The first MLP is to estimate the structural encoding, and the second MLP is to leverage the structural encoding and do the actual link prediction or node classification job. The teacher-student model happens in the first MLP. So now let me quickly show you some results we tested in our paper. So more experiments can be found in our paper published in iClear 2022, and our code are also publicly available in Amazon's code base. So we use our own internal e-commerce data, and the teacher is a two-layer GCN, and we tried the vanilla MLP solutions and our solution, which we named the Code Brew. So let's first look at where our most interest, the isolated node with absolutely zero connections. We have found that in 4 different partitions of our internal dataset, the MLP-based solutions from previous literature seem to work. So here, let me clarify. So here we set our GCN numbers to be the baseline. So you see the GCN is we denoted as 0 here. We didn't disclose this number because this belongs to our internal baselines. But all other methods numbers are reported as a difference, gain or losses compared to this baseline. So that's why you see the GCN to be 0 and all the others to be plus and minus. So we have found that for this absolutely isolated node, actually MLP methods are able to outperform GCN because GCN already have no good thing to aggregate. But by using our teacher model here, by explicitly consider error compensation, seem to slightly outperform the GCN teacher. But what really impressed us is by this teacher-student distillation, and when we switch to using student MLP on the isolated node, our student MLP could improve node classification accuracy up to 11% accuracy on the absolute isolated node. We also observed a similar benefit when we come to the cold start node. Well, the link there are some links, but they are sparse, but not and very noisy. In this case, we are still outperform the previous best method by 3% in accuracy. And on the head node, we find that GCN still gains advantage because now the link structures are there, and the link structures are useful. So while we still observe that the student MLP start to drop performance on the node portion of good head, we observed that our teacher GCN here actually improves over our original GCN. So actually, our current way is to switch between using the teacher and the student. If we have enough structure connections, we use the teacher GCN, which is stronger than normal GCNs. If we come to the isolated and tail part, we will switch to use the student MLP, which give us big gains. So that has been improving our code start recommendation and search tests a lot. With that, I'm ready to conclude my talk, and I appreciate again for having me here for the talk. Thank you.
Thank you very much, Alice. Any questions from audience?
Ying, I think this question was requested to skip the QA because
okay.
we have PR requirement.
Okay, great. Thank you very much for your attention. So, thank you.
Thank you. You have a good day. Bye bye.